Okay, let's get started, everyone. So let's start with some quick updates on logistics. We should have your project proposal feedback very soon. I am the culprit. My TAs have done most of their feedback, and I'm still working on mine. So hopefully we'll be done by the end of the day, or by tomorrow at the latest. Regarding your exams, we have a few people taking makeup exams later this week. So once they're done and their exams have been scanned, it should be pretty quick to release the grades, since Gradescope has like an auto multiple choice grader thing, which is super convenient. That said, you should check over your, when you get your grades, check over your each question to make sure it properly associated your answer choice with the answer. We'll release the solutions so you can do that. Okay, any questions? This class is so empty compared to... I feel like I hadn't even seen half of the people that were... Okay. So let's start. Today is actually a very important lecture for probably most of your project. So we're finally going to be switching from pre-training and all that architecture stuff that we talked about to post-training. So now we assume that we know how transformer language models work, how we do backprop, etc. Now we're going to get into how do we actually make things like ChatGPT, like that, follow our instructions. Let me just make sure this is working. Okay, I assume it is working. Oh, what happened to my cursor? All right. So we have two different topics for today, like at a high level. The first is instruction tuning, and the second is parameter efficient fine tuning. So in the course of this lecture, we will cover fine tuning, which is commonly now called SFT, just abbreviated supervised fine tuning. Then we will also cover kind of efficient ways to perform fine tuning that allow you to do like fine tuning of pretty large models on maybe not your laptop, but you can certainly do it on Colab or with pretty cheap GPUs. So pre-exam, we focused entirely on transformers up to pre-training, right? So when we were talking about pre-training, we had an emphasis on huge scale data, giant models, right? We were talking about scaling laws and how basically bigger data and bigger models makes our training loss, it's predictive of the test loss decreasing. But at the end of all of this training, we are left with a good next word predictor, but not so good at following our instructions. So, we did a couple demos throughout this semester where we took that giant llama 405 billion parameter pre-trained model and put in a bunch of different instructions to it, and we saw how sometimes it just wouldn't follow them at all. Other times it would kind of follow them, but also do additional stuff that we didn't want. That's because these models are completely optimized to being good next word predictors on this giant data set. And the giant data set doesn't really contain a lot of examples of instructions paired with the intended output of following that instruction. So that's why you have this kind of behavior of pre-trained language models. So if you just pre-train a giant model, you're not going to have ChatGPT, right? And so we want to get to a point where the model is following our instructions more, but also important, especially for certain labs, is the ability to control what the model does and doesn't respond to, right? So there's concerns of the model's outputs being harmful, right? And in the interests of safety and so on, model developers can choose to inject different behaviors into their model. So all of this, instruction following and safety alignment, is under the umbrella of post-training. And so, broadly, our focus for the rest of the semester is going to be on various things related to post-training, and your second exam will likely primarily be about different post-training methods that we discuss for the remainder of the class. So the high-level goal here is to make the pre-trained model follow user instructions better. So we will see, like, early on in this next block, we will talk specifically about very concrete instructions, like write a story about this. Later on, we'll start talking about agents that are powered by language models, where the goals may be more kind of abstract, like analyze this collection of websites and give me a report on interesting findings, where you might have multiple calls to a language model, and you might have a language model kind of orchestrating those calls and seeing what worked, what didn't, continuously issuing more and more calls until some task has been completed to whatever level of satisfaction you define. So we're going to, see things getting increasingly more complicated in the post-training landscape. How do you train such agents? How do you evaluate them? And so on. But for now, we're not there yet. We'll just focus on following single user instructions better. And then, as I mentioned, a sub-goal is to make the model aligned with human values, for whatever definition of human values you want to choose. You will see this term alignment over and over in different papers and model releases and so on. Most of the big labs have teams dedicated to alignment. Because at the high level here, there's a trade-off between helpfulness and harmlessness. So you want your model to be maximally helpful until there is some, unless there is some, issue with the prompt, right? Like maybe you're asking how to build a bomb or something, right? And you don't want your model to give you detailed instructions on how to do so. However, we can see that when you try and make a model harmless and you kind of censor its outputs and make it abstain to different things, it's not exact science, right? And so sometimes you might observe your model abstaining from things that are not at all offensive or harmful in any way. So there's one side where you want your model to be super high performing on tasks that people care about, and you want it to generalize to new tasks. And on the other side, you want the model to kind of be aware when it shouldn't behave in a certain way. And that trade-off is a area of very active study. All right, so I want to go over the general post-training pipeline. We've seen this figure before when we talked about pre-training, but I'm going to just draw it again and then kind of use it as a roadmap for the rest of the semester. So what we've covered so far is essentially step one of creating a large language model. So here we start with a completely randomly initialized language model, right? So this is a transformer with all the weights and embeddings initialized to random numbers. It cannot do any reasonable job of predicting the next word or following instructions. And so what we've done is we've exposed this to a giant data set, and we've done pre-training on it to predict the next word in this giant data set. And as a result, we so far know how to obtain this pre-trained LM. So this is our first step that we've covered so far in this class. Now, there are, unfortunately, in post-training, there's like millions of different things that you could actually do to this pre-trained model. You can fine-tune it on individual tasks. You can fine-tune it in general for instruction following. You can do reinforcement learning. There's so many different methods that people have developed. So it's hard to give kind of a as clean roadmap of post-training. But at a high level, we can maybe decompose it into two steps, like two high-level steps. And note that many models may have way more than two steps. They may iterate over these two, or they may merge them into one. But things that you should be aware of at least are, so in all cases, in the second step, when we start post-training, we will start with our output from pre-training. So this allows us to kind of reuse all of the useful linguistic information that the pre-trained model has learned, all of the facts about the world and things like that that the model has memorized in its parameters. Now, it's common to do instruction tuning here. You will also see this referred to somewhat confusingly as SFT. So this stage requires the collection of a diverse data set of input instructions and outputs on how to follow those instructions. The data set here is going to be nowhere near as big as the pre-training data set. So I'll write that. Smaller, much smaller data than pre-training. Because it's kind of, you're limited by how much data in this format that you can get, right? It doesn't really naturally exist at scale like general text does on the internet. So a lot of these big labs spend hundreds of millions of dollars just on data costs. So they hire people to label these things. They then see if they can use their own language models to synthesize new data like this and continue to train their models. So this phase has a lot of active interest as well. So at the end of this, you get an instruction-tuned language model. And so here, remember that in all of these cases, you're not adding new parameters to the model, right? From this first part where we randomly initialize this transformer, the size and architecture of the model has been fixed. Now, the only thing that's changing in any of these steps is the values associated with each of the parameters in the model. So they change once during pre-training. They now change again during fine-tuning. Finally, at the third step, we will start with our instruction-tuned model. And we will perform reinforcement learning on this model. And there are many different RL algorithms that people have proposed to deal with this. Oftentimes, this is a way for injecting human preferences. So commonly people will take a bunch of generations from the instruction-tuned model, send them to human annotators, and the human annotators will say, I like this generation better than this one. And that will get incorporated into this reinforcement learning phase to continue to encourage the model to generate responses that humans prefer. So that's kind of like the high level of this. And after several rounds of this process, we get the final output of, let's say, the final ChatGPT or Gemini model. I will just emphasize again, things are not this clean in practice. These two phases, steps 2 and 3, can be repeated over and over again. If a company, like let's say Anthropic, evaluates their new Claude model and finds that on, let's say, multiplication of 8-digit numbers, their model is worse than GPT. Now, they're not going to just like redo all of these steps, right? What they are going to do is collect data for 8-digit multiplication, and they will repeat either step 2 or 3 on that specific task to try and make their model better than ChatGPT. Now, there's a problem with that because if they improve their 8-digit multiplication performance, they might simultaneously degrade their 5-digit division performance, right? So they have to keep doing rigorous evaluations every time they kind of patch one of these different tasks to increase the performance to make sure they're not hurting other tasks. And so if you look at modern large language model labs in industry, most of the people who work there are engaged in this job of basically figuring out what their model is bad at and then patching the model's performance on those tasks to try and raise the performance to be competitive with other models, making sure it doesn't mess up anything else. And as you can imagine, there's a lot of tasks that people care about. So this evaluation and iteration process is hugely expensive and time-consuming. All right, so with all of that, today we're going to focus on this step here, and later on, next week, we'll start talking about reinforcement learning. Yes?
There's a step here on your screen.
Oh, okay, so annoying. Yeah, I got this laptop from UMD. I bought it through UMD, and they don't let you have admin privileges unless you like use this dumb app, so I get all these messages. It's very annoying. But anyway, let us continue. I'll just check here. Oh, where's my cursor not working? Okay, seems like no questions. Okay, so let's get started with first, just introducing the concept of fine-tuning, or SFT. And the idea here is that you take a pre-trained model, and in the general fine-tuning case, you collect a data set, of input, output pairs for a specific task. Now, we will modify this definition a little when we get to instruction tuning. But for now, and in general, if you only care about one task and you want your model to be as good as possible on that task and you don't care about any other task, this is the way to go. Collect a data set for this single task. So let's say maybe we only care about adding numbers up to 4 digits in length. So maybe I would collect a data set that looks something like this, where this is my input, this is my output. I hope that's right. This is my input. This is my output. And, I could collect or create millions of examples like this and just fine tune my model, and then hopefully at some point it will have learned this task. So you'll notice here that this isn't really like how you would use ChatGPT. This is more like demonstrations of a task that you would put into a prompt for in-context learning. There are no natural language instructions associated with this task. Here we're just saying this is the input you can expect. I don't care that you can. I don't care if you can solve any other task. I just want you to solve this addition problem. Okay, so let's say we have this data set for whatever task, addition or sentiment, classification, or topic labeling, or anything that you care about. The next step is train model on your data set to minimize the negative log likelihood on the output tokens. So here, remember that in actual usage of a thing like ChatGPT, we expect the model to be provided with some user input, right? So in this case, it would be 15 plus 128. We don't want to do next word prediction on the input. We only care about generating the output. And so here is a situation where we may want to use our prefix LM mask during this training process so that the model has kind of, in the prompt tokens, the ability to look at all the other ones, but then in the response tokens, it's still doing word by word generation. Yeah.
So when the model the prompt tokens can look at the other ones, or?
Yeah, the prompt tokens can look at the other prompt tokens because we're not doing any generation of prompt tokens, right? It's just the response tokens that you don't want to look at, right? Because those are the ones you actually want to generate. Yeah. So if you'll notice here, we've basically changed nothing about the pre-training setup. We have just modified the data, and we're also not computing a loss on some of the tokens, right? We're not going to compute a loss on any of the prompt tokens, just the response, the output tokens. Does that make sense? Yeah.
So before when we use like prefix LM, did we also compute the loss for the prefix also?
No. So in the prefix LM case, we are assuming that everything that is doing like unmasked attention, so all in the prompt, we're not doing any word prediction. Because if we were, we would have full knowledge of what is coming in the future.
So we wouldn't compute the loss?
Yeah, you don't compute. You only compute the loss over the response tokens, the output tokens. Okay, great. So just to clarify, basically same as pre-training. We're just differing in the data and the mask. And then also note that in pre-training, we start with a randomly initialized transformer. In fine-tuning, our parameters are initialized to the pre-trained model. So we already start with a pretty good model. And that's why it's kind of called fine-tuning, right? You expect your model to already be pretty good, but kind of rough around the edges. And the fine-tuning will hopefully just make it better on certain things that you care about. But it's already like pretty decent at it, yeah.
So when we were going over the prefix LM before, were we always going over that in the context of that being part of post-training, or was that always pre-training?
So I went over that mask just to set up that it would be used in these cases and in things like ChatGPT. So also at test time, right, if you receive a prompt, there's no reason for you to do masking on the prompt tokens. You would benefit from having each prompt token look at the future prompt token since you're not generating. So yeah, that's a good question. Yeah.
So you said that it differs also in mask, but I mean, like, I feel like it's just how the mask made it.
Yeah, right. In pre-training, we use the diagonal mask, right? And so here we have some variation for the prompt, but it's basically the same thing. Yeah. Yes.
So when you train on this new data set, do you not like look at the old data set anymore? You only train on the new one, or do you kind of intersperse the old?
Yeah, that's a good question. So here, when we're doing SFT, we are generally only looking at the new data, and we're not going back and doing more pre-training on. That said, there are some cases where you would want to do more pre-training. So for example, if you want to increase the context size of your language model, you can do what's called continual pre-training to, unlike longer documents, to lengthen the context size. But in general, we're not doing that, yeah. Okay, oh, yes.
So I'm wondering, what if you forget to apply the prefix LM mask?
That's a good question. So if you don't use a prefix LM mask, you're not going to change very much. In fact, for many cases, it could be exactly the same. You would just be predicting the next prompt token as well. It might be an issue if your inputs are very, very long and your outputs are short. So let's say I ask, like, is this statement about this book true or false? And then I have a huge book in my prompt, right? Now my loss is going to be dominated by predictions on the input, not really on the task that I care about. That's just a very small, like maybe one token. So yeah, there are some cases where you want to do that.
So here, as you mentioned, there's no like words in the input and output. Is that true a lot, or?
Not necessarily. This was just a easy example, but it could be like translation, for example, where the input is in French, the output is in English.
But it's just like the input being like one, like sort of like, I guess it's not like text that.
I mean, here, like any string we've talked about, like can be tokenized using various methods,
No,
right?
but what I mean is like it's not like. It's like completely different from the pre-training stuff.
Not necessarily. Like there are a lot of math papers and tutorials and stuff like that in the pre-training data. So just pre-trained models can already do arithmetic to some degree, and so it's hard to conceive of like what is actually in this giant pre-training data set of 50 trillion tokens, right?
I guess like here it's like. Here it's exactly what we want instead of
Exactly. Yeah, but that brings up a good point, which is that when you do SFT, you risk what's called catastrophic forgetting. So essentially, your model will become very good at the task that you care about, in this case, like addition, but it will lose its abilities for other tasks that it acquired during pre-training. So it might lose some factual knowledge, it might lose the ability to translate or write stories or whatever that base model had. It might become very good at the one task that you fine-tuned it on, but really bad at all the other tasks. So you should only do SFT in this way if you really just want to maximize performance on a single task. Otherwise, if you want like a general purpose chatbot like ChatGPT, you need to be very careful about this stage in your data collection, as we will see. Does that make sense? Okay. If pre-training is also done using prefix LM mask, is post-training actually anything different? So this is, just to clarify, in pre-training we are not using the prefix LM mask during training. We're using the full like diagonal mask because we're just trying to do next word prediction. We don't assume that we have a prompt of any sort during pre-training. It's only during post-training where we start observing inputs and user-provided prompts that this becomes relevant. So that's a good question. Okay. So what am I doing now? Yes. So let's say moving on, we want our model to be a general purpose chatbot. So we want it to be good at a bunch of different tasks, not just one. So this introduces the concept of instruction tuning. So this is literally the same thing as SFT, but the data contains a huge diversity of tasks, so not just one task. And it's also kind of formatted differently. So the format here for the input is like an instruction, then some input context if needed, and finally we have an output. So for our example above, this instruction could be add these two numbers, and then this context could be 127 plus 13 or whatever, and our output could be 140. So here you see that if we want to have many different tasks, the instruction is what allows us to differentiate the purpose of each task, right? So here I have add these two numbers, but I could have a completely different task that may be in the same data set. So let's say this is our example 1. I could also have, solve my homework 2. And then the input context could be homework2.pdf. And the output could be the, Python code for homework 2. So you can have, like many different kinds of instructions, input context, and then target outputs. There are many instruction following data sets. So if you're interested in doing instruction tuning, you can go to Hugging Face and look for data sets that include a bunch of instructions. One very large one put out by the Allen Institute is called Tulu3. It's got like 1 million of these instruction following examples. So I wanted to just show that really quickly. So let me do that. So this is the Hugging Face page for, Tulu3. I'll try and make it bigger. So these are kind of some data points here. Here's one. Can you summarize me a story from the book Harry Potter and the Philosopher's Stone? And then you have output here. You can see that now, and you'll see this in general if you're doing fine-tuning, is that some of these models expect a particular format of the data where some things in the input are user messages. So in this case, this is a user message. It's an instruction from the user. And the response is from this assistant role, which is like the AI, right, the LLM. So how this gets kind of, these roles get embedded into the context is through special tokens. So you might have like a special user tag followed by all of the instruction text, and then an end user tag, and then an assistant tag, and then the response, and so on. So different models that have been released have different formats for instruction tuning and have different roles. There's like system messages, there's assistant messages, and so on. And this is actually a very common source of errors when you're doing SFT. You need to be careful to use the right chat template for the model, otherwise it might behave very strangely. So some of these have multi-turn interactions. So here the user is also asking for a recommendation of books that are similar to the Hitchhiker's Guide, and the model generates this. One thing also to note is that instruction tuning in these kinds of data sets is not only a way to teach the model to better follow instructions, but also a way to kind of teach it the general format that those responses should take. So if you've used ChatGPT a lot, you probably noticed that it says like certainly exclamation point a lot. And one way to encourage that behavior is to put a lot of certainly exclamation point in the instruction tuning data. So there's a lot of like weird quirks of these models that arise through fine tuning, like a model's choice to use M dashes a lot, right? Maybe they had a lot of labelers who liked M dashes, and that's why that happened. Who knows? But like clearly, whatever is in this data has a large impact on the model's behavior. So you can see that there's a lot of non-English instructions and outputs. There's more constrained ones. Don't know what this is, so on. So like there's millions of these in data sets like these, and if you're interested for your project, you can check out any of these. All right, so let's go back to the iPad. So now I wanted to get to some of the issues of instruction tuning that are mirrored in pre-training, which are essentially if your model is really big, it's going to be hard for you to do instruction tuning or SFT, even if your SFT data is small, because you still have to load all the model's parameters into your GPU memory. You then have to compute gradients all on your GPU. Then you have to do the update process. So if you have like a 405 billion parameter model, like that Llama one that we were playing around with, you're not going to be able to load that to do inference, let alone do backprop during SFT. So this is a major problem. Not only for like us, right, individuals who just have laptops and so on, but also for anyone who's not like an OpenAI or a Google or an Anthropic that has tons of GPUs, right? Even other big, well-resourced industry firms have this problem where they want to, do some large-scale training or SFT, but it's just hard to do it with the resources that are available. So overall, the problem is that SFT, and SFT here I'm just going to use interchangeably for instruction tuning moving forward, but it generally applies to whenever you're doing fine tuning of a model. SFT on huge pre-trained models is expensive. It requires a lot of memory in GPUs. And why is that? It's because you're adjusting billions of parameters through backprop. So the memory costs are super high. And this kind of motivates this line of work on parameter efficient fine tuning, which we often see abbreviated as PEFT. I have never actually pronounced that, but PEFT, yes. The goal here is to reduce the number of parameters adjusted during fine-tuning. Parameter-efficient fine-tuning often goes hand in hand with methods like quantization, which we'll also talk about towards the end of this class, where you're trying to reduce the entire memory footprint of the model by compressing it down to like integer weights instead of floating point weights. But we'll talk about a couple parameter-efficient fine-tuning approaches in this class. We'll start with probably the simplest and cheapest, but also worst performing one, which is simply just prompting. So here, no parameters are adjusted, which is a huge win. And you can control the model's behavior by modifying what you choose to put into its prompt, right? So control behavior by modifying the prompt. And the prompt here is essentially the prefix that we've been talking about during pre-training, like what is the input of the model. You can put demonstrations of how to perform tasks into the prompt. So this could look very similar to instruction, input, output, like your actual fine-tuning data format. You just shove many examples of that into your prompt and then see if your model can generalize from that to new examples. And so through this process, you can kind of teach a pre-trained model to solve a new task without adjusting the parameters at all, but it fails for very complex, well, I shouldn't say very, let's just say complex tasks, and also requires extremely large pre-trained model. So we already saw the 405 billion parameter pre-trained llama model. We can prompt it however we want, but it is not likely to, always follow our instructions. Did you have a question?
Yeah. So does that mean that like when the user uses it at the end, they'll have to like adjust the prompt for that?
Yeah, exactly. That's another thing. So if you find, there's only this one prompt that seems to result in good performance on addition, then you need to tell the user this is the prompt you need to use if you're doing addition, right? Which is very clumsy. And so this is not a good solution for if you're just sticking with a pre-trained model. Obviously, this is the solution that we eventually want, right? We want users to be able to specify their task in natural language and have the model follow it. But we need to get the model to a stage where it's able to do that. And the pre-trained model is not the place where we can just rely on giving instructions in the prompt with no further training and have the model generalize. So this is, not a great way to solve the problem. So another approach, which requires more training, is called prompt tuning. And this was introduced by Google a few years ago. And one of the benefits is that we freeze the entire model, and we add small number of new parameters that are fine-tuned. So when I say freeze, that means during the training process, we do not update the WQ, WK, WV matrices, the feed-forward layers. All of those are kept identical to the pre-trained model's parameters. That said, we have to train something in this case, and so we're going to add a very small number of new parameters to our model that we're going to adjust on the fine-tuning data. So how does this work? Let's say I have this input, let's say solve my homework 2, and then my intended output is, I don't know, like solve homework or something like that, and it goes on. So now, like, our pre-trained model can take this input, right, and it'll embed all of these tokens. It'll pass them into this, pre-trained transformer. And here we'll use our prefix LM mask so the prompt tokens can look at each other. And finally, we'll get these final layer hidden representations. And now here, we're going to be predicting the next word only on our response, right? So this token, I'll predict def. Here, I'll predict solve. Something like this. So I can fine-tune my model like this. If I wanted to do supervised fine-tuning, I would take all of these losses and backprop into the entire model and adjust all the parameters. But in prompt tuning, it's going to be a little different. So my what's going to happen is, first, at the beginning of every input, regardless of what that input is, I'm going to prepend 2 new embeddings. So we'll call these E1 and E2. These are not associated with our vocabulary. They are not associated with like word types in our vocabulary. They are just new parameters that are prepended to our input. And for every single example, the same 2 embeddings are prepended. These are also the only parameters that I'm going to be updating during fine-tuning, are these 2 embeddings at the very bottom of the network. So how this works is, change this to a dotted line. So when I'm computing my gradient, I still will start at the very top, right, at the output layer with all of the words that I'm predicting. I compute a loss of how good was it at predicting this ground truth word, and I aggregate that signal, backprop it down into my entire model where it goes all the way over here, and I can compute these 2 partial derivatives, dl de1 and dl de2, right? So I'm going to look at the partial derivative of the loss with respect to each of these 2 new parameters that I have added, and I only want to compute these, and then I will update them. So E1 new equals E1 old. And so on, right? And so now all of the parameters in this model are frozen, and I'm only adding these like tiny embeddings at the bottom. So that means that E1 and E2 basically define all the new tasks that I'm going to be training my model on during this fine-tuning stage. So you might be like, well, how does this even work? The entire model is fixed, and I'm just adding these 2 random embeddings, and they're just supposed to kind of imitate the prompt or the instruction and help the model solve the task, even though they're not even real words and we're in the vocabulary. That said, this approach works surprisingly well. It's really unclear what is happening in these new embeddings that are prepended. They've tried to like interpret what are the words that are closest to these embeddings in the vocabulary. It generally seems to make some sense, like they correspond strongly to embeddings that are similar to the task that's being fine-tuned on. But yeah, it's very interesting that this process works, and more so it works better when the pre-trained model is larger. So you have more parameters. Somehow that's able to, that makes the model better able to take advantage of these new parameters. You have a question?
What was the intuition between somebody trying this anyways, like for the first
I think it was like, built off prompting, where you essentially are specifying these new embeddings in natural language, right? So these are the instructions. And they were like, well, you know, if I'm doing prompting, I have to try manually a bunch of different prompts, and it's hard for me to find the optimal solution. What if I just let the model learn these prompt embeddings? So that's the intuition, but it's very surprising that it works. Yeah.
So when you're, sorry, I have another question actually.
Okay, no worries. Yeah.
So what if instead of adding 2 new embeddings, we added like another layer on top that is not pre-trained, it's randomly?
Yeah, that's a good question. So that is actually also a popular, it was at least a popular method for fine tuning, where you keep the entire model frozen and then you just add a new layer on top. Actually, more common than that is you keep the entire model frozen, but you just fine tune the topmost layer. So here you're not even adding new parameters. So actually, if you look at this paper, they do try that version, and they find that this is better. Possibly because these new embeddings are able to interact with every single layer of the transformer. And so you might have just like more nonlinear transformations of them. But yeah, it's also, you know, actually, if you think about it, this method, prompt tuning, is actually still pretty expensive, because to do backprop, you have to compute the gradient all the way back down to the bottom. Whereas in the method of just fine-tuning the top layer, you can stop after the top layer. So it saves you some gradient cost.
Sorry, so when you're doing this, you're kind of giving up on all the pre-training you did. You're like really forcing the model to this very niche application at this point, right?
Well, this could happen for instruction tuning as well. So if we have a large, diverse collection of different tasks with instructions and so on, you can still do this. That said, the paper originally was focused on specific tasks. So yeah, you're
Even in the instruction tuning case, though, you're kind of making it that everything is forced through the lens of instruction with these added.
Yes, that's right. The one intuition, though, is because you're not modifying the pre-trained parameters, you kind of help the model retain most of its abilities, versus fine-tuning where you could simply erase some of the knowledge because you're overwriting the parameters during pre-training. So they do show that this model has more robustness than, fine-tuning.
So to be clear here, we're only computing loss for E1 and E2. So those are the only things that are.
We're only computing the gradient for E1 and E2. The loss is computed over all of the output. Yeah. Yes, that's correct.
So we only change E1 and E2, and the rest of the model stays the same.
Yes, and it still somehow works.
But we still have to compute all those gradients.
Yes, you have to compute. Sorry, I should say we are only using DL DE1 and DL DE2 in our update rule. But we still have to compute all the higher level derivatives in order to get DL DE1 and DL DE2, because we are doing it through the chain rule. Yeah, so it's not saving us compute cost, but it is saving us kind of like the space on the updated model. So if I wanted to share my fine-tuned model with someone else, in this case, all I have to do is send them these 2 embeddings, right? They have the pre-trained model. Whereas with normal fine-tuning, I would have to share the entire billions of parameters that I've adjusted. So that's a big advantage in this case. Do you have a question?
If we view this prompt as a prefix, so what's the difference between this method and prefix tuning?
Oh, so we haven't talked about prefix tuning. Are you referring to the paper about prefix tuning, or what do you mean by prefix? There's a method separate of this called prefix tuning that is pretty similar to this, but we're not going to talk about it in the class. Yeah.
So here, do we always introduce 2 new embeddings? Or
No. So that was just what I could fit on the. It's actually a hyperparameter, right? How many you introduce, and some common ones are 1 embedding, 5, 10. They actually show in the paper that adding more after a certain point, I think like 10, doesn't help anymore. So a lot of tasks seemingly can just be defined in 10 embeddings.
So it's only a small one.
Yeah, very small number of new parameters. All right, let's see on here if you have any questions. Is this a stage where you can add watermarks to detect if an output is LM generated? We will talk about watermarking later in the semester, but in general, watermarking is applied to the final post-trained model after all of this stuff that we're talking about so far. So we'll get back to that. All right, so prompt tuning is cool, but it's not the most popular parameter efficient tuning method. That is something that you all will likely work with, or many of you will work with on your project, called LoRa, which stands for low rank adaptation. So when we're comparing like full fine tuning to prompt tuning, LoRa is more in the middle, where you're adjusting more parameters than prompt tuning. It leads to better performance, and it's much closer to full supervised fine tuning. It does require more space than prompt tuning. You can't just send 2 embeddings here. You have to send more parameters over. But performance is better, and this is nowadays the most popular method for both SFT and also increasingly for reinforcement learning, as we'll see later. So I want to go over this in the last 15 minutes here, and then maybe if we have time, talk about quantization as well. So when explaining LoRa, it's good to just take a simple linear layer, right? So our something like this, which we see a lot in the transformer, right? Every query key value projection, every feed forward layer has this form. And so let's say that the dimensionality of W here is M cross N. Where M and N are both generally pretty large, right? It could be like 1024 by 512, or some like huge number of parameters are generally in this matrix. And remember, our goal in these parameter efficient strategies is to reduce the number of parameters that we are actually updating. So if W is M cross N, then DL dW is also M cross N, the gradient, right? So when we do our update, so W new equals W old minus our learning rate, DL dW, this thing is M cross N, this thing is M cross N, and so there's a lot of memory and storage associated with this whole thing. So the idea of LoRa is, what if we factorize W into 2 low rank matrices, which we'll call A and B. So the general idea here is that the update that you get when doing fine tuning is lower, or it can be approximated by some low rank matrix. So here, A is going to be M cross R, and B is going to be N cross R. And so R is the rank here. It's generally set to something like 4 or 8 or 12. So R is much smaller than M or N. And so the idea is that if I have, let's say, 1024 by 1024 matrix, I can decompose it into 2 matrices that are, let's say, 1024 by 8 and 1024 by 8. In doing so, I save a ton of parameters. Of course, the approximation here is with this matrix product. So matrix product A times B transpose is also M cross N. And so the approximation that we're making in LoRa is this linear layer, h equals f of wx, becomes h equals f of w pre-trained. So this is the w that we have in our pre-trained model, plus this product of these two low-rank matrices. And then we have our x over here. So we have essentially this learned additive offset. So instead of doing the full DLDW, we now have to compute in this new form DLDA and DLDB. And we will keep this frozen, meaning we're not going to compute the full DLDW. So all we're trying to do is learn these A and B matrices. And then we will add the product of them to our pre-trained matrix, and that will be our new fine-tuned parameters. Does that make sense? Does it make sense how this formulation can save a lot of new parameters that were, new partial derivatives that we're computing? Because DLDW has a ton of parameters, but DLDA and DLDB are much, much smaller. If that's not clear to you, you should work this out yourself, do a simple example to see exactly how much you're saving here. So just again to restate, these are much smaller than DLDW. Both of these are M cross R and N cross R, where R is very, very small. So in general, this is for one linear layer. We can do this for every linear layer in our pre-trained transformer, right? So we take the pre-trained weights, we keep them frozen, we learn a separate A and a separate B for each of the W matrices in our model. So separate A, B for each weight matrix in our model. And also, if you look at the standard implementations of LoRa in like Hugging Face and other libraries, you're not actually going to apply this to every weight matrix. In fact, they select just the projection matrices in the attention, the WQ, WK, WV, to apply these two. And they leave the feed-forward layers fixed, and they leave the embeddings fixed and meaning frozen. So this method, LoRa, achieves very, very similar results to full supervised fine-tuning. And just like in prompt tuning, the advantage is to share your update with someone. You just have to send them your collection of A and B matrices, right? You don't have to send them the entire pre-trained model, the entire fine-tuned model. If they just have the pre-trained model, you can send them this update, and they, magically have the capabilities of your fine-tuned model. So this is kind of a middle ground between prompt tuning and full fine-tuning that has become by far the most popular setup for parameter-efficient fine-tuning. Okay, any questions about this? Yeah.
Why is it smaller? Because like I think the matrix AB transpose will still be M times N, right?
Yes, AB transpose will be M times N, but it is factorized into two much smaller matrices, right? So you have, in your storage, you're storing A and B, right? These are the parameters of your model. If you count them up, there are way fewer parameters there than in M cross N. So the model still has to form this M cross N matrix AB transpose during the forward phase, but regarding the parameter count, it's much smaller. All right, so in the last part here, let us quickly talk about quantization. I should add also, last thing about LoRa is, so this is how we're doing training, right? At test time, our final model, so let's say W fine-tuned, we're just going to take the pre-trained weight matrix for all of like WQ, WK, WV, all the things that we're applying LoRa to, and we will simply add the AB transpose for the final A and B matrices associated with this. And then to do forward propagation at test time, we are just going to use this fine-tuned WFT, which we obtain by adding our LoRa parameters to the pre-trained weights. So it's a very clean formulation, but still have to fit W pre-trained in memory. So this is the same concern that you brought up. You still have to fit this M cross N matrix. And that's where people have turned to quantization. And we will, because we have 5 minutes, just talk about this pretty intuitively, but I also go through a simple example. The intuition here is like our parameters of our model are generally in floating points, floating point numbers, right? So we spend a lot of storage to keep each of those parameters in our memory. If we could simply somehow like round our decimal numbers to integers and make it such that we have very few unique values that a parameter could take, then we could save a bunch on storage costs, right? Instead of, let's say, a float 32 or a float 16, what if we stored this in a 4-bit integer that has 16 unique values? Each parameter could be stored in such a manner. If we don't, lose a lot of performance, this is a great way to save costs. So the intuition is basically rounding our floats to ints and doing some scaling. There's many different quantization methods proposed. I'll just go over a quick one so we understand like what we're talking about here. So let's say x is a vector, and it has some floating point value. So let's consider this as, say, maybe an embedding in our model. So we have some floating point values. And we want to quantize this into int4, so 4-bit integers. So 4-bit has 16 different values for each parameter. And so obviously we can't really store these, the current vectors in int form, so we have to do some rounding and some scaling in order to achieve that. So first we've got to choose like some range of values. So for int4 we have the integers from 0 to 15. And we want to get all of our parameters into assigned to one of these 16 integers. So what you can do in the very simple like affine transformation of this vector is first compute the min and max of this vector. So in this case, and in practice we will be doing this over all of the parameters in our language model, compute the min and max. We'll have to do something to deal with outliers, which we're not going to talk about here. But in this simple example, our min is -1, our max is 2.0. And so now we can use the min and max to determine a scaling factor so that we use all of the integers in our acceptable range. So here we can just make a simple scaling factor, which is the max minus the min over the number of bins we have. So maybe you can divide this by 15. So we get 3 over 15 equals 0.2. So I guess this should be like number of bins minus 1. And so this means that every time we increase by 0.2, we will assign a number to a different integer. That's the scaling. We also may want to figure out where our 0 point is going to be. So here we can just set this to round x min over s, which, sorry, this should be a minus, equals 0 minus, and our minimum is minus 1, our scale is 0.2, this equals 5. So here in this example, we will set 5 to be our 0 point. So anything above 0 will have a value above 5, anything below 0 will have a value below 5. So now, in this simple quantization strategy, to quantize a new number, I'm just going to round x over s plus z, and this will get me one of those integers, one of those 16 integers. And to recover the original value of the quantized number, all I have to do is multiply it by the scaling factor after subtracting the 0 point. So we'll just finish up by looking at what happens if we apply this quantization strategy to our x vector, which used to be minus 1, 0.0, 0.5, 2.0. If we do quantization, we get 0, 8, and 15. So these are our new weights. We've quantized this into 4-bit. So the thing is that when we recover the weights, we always will lose some information. So when we want to actually do forward propagation with this model, we're going to need to recover some weights, or when we're doing backprop. And using that formula above, we do manage to recover 1.0 exactly, but we get 0.6 and 2.0. So we have some loss compared to the original parameters. The trade-off is that this is, results in much smaller storage footprint. And so many of the models that you will see today for download are quantized into 4-bit or 8-bit integers, and they work really well. And we also see that larger models, when they're quantized, seem to work better than smaller models. Okay, so with that, we will end for today, and we will talk about reinforcement learning next week. So stay tuned. Hi.
So for instruction tuning, because we have instruction, input and output, do we need to change the structure of the model? Like, how do we train the instruction part?
Well, it's always assumed that the instructions are coming from the user. So
Basically, so instruction is one part of the input as well.
yes, that's right. And as I showed in the Hugging Face Tulu 3 example, they might be associated with different tags or roles, like user role, system role, things like that. So those are all special tokens. But yeah, in general, they're treated as part of the input, and nothing else is special about them.
But then we need another procedure to, suppose I just say something, put something into ChatGPT. So I didn't specify which part is instruction, which part is input.
That is, it's all considered the same here. There's nothing special about the instruction versus the input. That's just kind of the format of the data that people are collecting for these instruction following data sets. The model treats it all as a single input.
Okay, sure.
Yeah.
Thank you.
Hi. Yes.
Quantization.
Yes.
So, for example, if we multiply all weights by some number, let's
Yeah.
say 1.001, will the output be okay, or it will be completely messed up?